In this last video of our introduction unit, what we're going to do is look at some common test waveforms that are used in that analyze and design step, which we discussed in the previous video in our overall design process. And so again, this is just so that we're all on the same page in terms of knowing what these various signals look like. The first one that we're going to look at is something called the impulse function. And so our impulse function is traditionally represented by delta, and so I'm going to say it's a function of t. And to be a little more general, what I'm going to do is put a constant value k out front of the delta. So if we were to plot this on a graph f of t versus t, what that's going to look like is just an arrow at our origin. So I can say this is k delta of t. Now mathematically it's a little more complicated than that, so our delta function, our impulse, is infinite valued at the origin, 0 everywhere else, and in this case our area under the curve would be constant value k. But again, we're not going to get too in detail with that mathematical definition, but what we should know is that in general this impulse function is used to investigate our transient response. So it's used for transient response modeling. And so what this means is maybe we have a physical system, we can send an impulse as an input, and we can see how the system behaves and then try to figure out how to model the system better. Or maybe we already have a rough model, so we can sort of simulate or do calculations of what output is produced when we have an impulse function, and then refine our model from there. The second type of function we're going to talk about is a step function. And so our step function is usually represented as u of t. Now again, I'm going to make things a little bit more general. So what I'm going to do is I'm going to say we have some constant value k1, and then we're adding to that some constant k2 multiplied by this step function. And I'm also going to shift the step function by some general amount t naught. Now, so what that's going to look like if we plot that, so let's come down here and plot this. And so of interest is going to be our point t naught here, so that's how much we're shifting by. And of course, we're going to be interested in levels k1 and k2. And so what this is going to look like is we're initially going to be at a level k1, and then once we reach this t naught point, we're immediately jumping up to a value of k2, and then we're staying constant at that value. And again, so I've just made this very general. If you take away the t naught, you take away the k1 and k2, we can see it basically is just a function that goes from 0 to 1 at the origin, and then it stays at 1, unlike our impulse function. So what do we need to know in terms of if we're using this for that analyze and design step? Well, our step function is commonly used for our transient response modeling, so just like our impulse. But it's also used for steady state error modeling. So I'm going to write that as SS error, so steady state error modeling. Okay, so a few more functions to look at. The next one we're going to look at is our ramp function. And so our ramp function is essentially just going to be t. Now, we're usually just going to be concerned with causal systems, so they're only defined for t greater than 0. So let's multiply this by u of t. And again, to make it even more general, we can put a k out front. Let me clean that u up a little so it actually looks something like a u. Okay, so we have something like that for our ramp function. And so of course what that's going to look like if we have this and we were to plot this, again, it's only defined for t greater than 0, so we're just going to have some linear line with a slope k. And this is going to be used in steady state error modeling. Okay, two more functions to go. The next one, sort of similar idea to our ramp function, is a parabolic function. And so that's just going to be t squared. But just like with our ramp function, let's define it for t greater than 0, so multiply by the step function, and multiply by a constant just to make it a little more general. And what we would see if we were to plot this is, of course, we're just going to have, as the name implies, a nice parabola, but we're defining it for t greater than 0, so we only have half of that. And again, our slope is going to be related to that constant term. So this is also used to help with steady state error modeling. So our final function, which we are going to use often, is a sinusoid. And so just like with the other ones, I'm going to make it a little more general. So let's look at a cosine function. And so let's say we have some frequency times t, so omega, which is a radial frequency, times t. But let's add a phase shift in there of theta, so plus theta. And let's also put some magnitude k out front of that. So it's just some constant value k. So what that's going to look like, we've shifted this by theta. So we're going to have our peak now instead of at the origin. Switch back to this. So instead of at the origin, we're going to have a peak at negative theta over omega. And so that's just the argument of t that makes this argument here equal to 0. And then of course we're going to have high and low values of k and negative k respectively. And we'll just have a sinusoid. So here's our peak. So we have something that is going to look maybe roughly like that. So of course that should be going down to our negative k there. And so this waveform, or this type of wave, or type of input rather, is also going to be useful for both transient response modeling and steady state error modeling. And so again, hopefully everybody was already familiar with these, but if not, hopefully that was a good refresher. So that's the end of our first introductory unit. In our next unit, we're going to start looking at how we can model systems in our frequency domain.